Welcome to Simerics. The following approach to pump analysis and diagnostics is a type of virtual testing, which has many advantages over actual physical testing traditionally performed in the typical manufacturing environment. The use of CFD and multiphysics modeling has long been proven to be essential for the optimization of modern design and manufacturing of pump-related devices. Using the virtual testing approach, the analyst will get all of the data as would be obtained by a physical test and more. The advantages of this approach are you have access to the whole flow field, not just a few points, so you have a complete and comprehensive understanding of everything going on inside the device. You can see here all of the flow quantities that are available after a simulation is performed using PumpLinx. And this is available throughout the flow field. It's quite an advantage over traditional testing. You can perform as many tests as you like, changing conditions or geometry as required without much effort. The virtual test approach is often more accurate since many of the traditional testing methods are intrusive and alter the very flow field they're supposed to obtain data from. Performing simulations is more cost-effective than laboratory testing as well. Here is a flow visualization of a transient solution of a centrifugal pump. The inlet has been seeded with particles in order to see the flow field. The purpose of this presentation is to set up a geometry in SpaceClaim, take it over into PumpLinx and run a simulation, then come back to SpaceClaim to modify the geometry, re-export it into PumpLinx, and show that the boundary conditions and the model setup is still there, even though you modified the model. So what you see here, this is the liquid volume, which has been split out from the solid parts of the pump, like the pump housing and impeller blades and so on. This is the impeller volume, and this is the volute volume. Before we go over into PumpLinx, we can take advantage of some of the features in SpaceClaim to make the model setup easier in PumpLinx. If we name the surfaces that require boundary condition specification here in SpaceClaim, we can skip the surface preparation steps in PumpLinx. So if we name this, well, these are already named, and this is where you would change the name if you wanted to. It'll come across in PumpLinx, ready to be identified with a boundary condition. Here's the outlet. These are MGI surfaces, which stand for Matched Grid Interface. The volute also has an MGI surface. This allows the two volumes to communicate across this interface with one another numerically. And we also want to specify a cell size, so we have the cell size on the surface and the maximum cell size. Same with the volute. It's already been set here. This is a way to control the refinement of the mesh before we mesh it. So now that everything is taken care of here in SpaceClaim, we will export this into Simerics and mesh it automatically. Since the loading process takes a couple of minutes, I'll just skip forward to PumpLinx. So here's the model in PumpLinx. And since we don't need these CAD surfaces anymore because we already have a mesh, I'll just close this. So now let me show you the boundaries that constitute the volumes. The impeller volume and the volute volume are composed of these boundaries. So let's take a look at the mesh. We'll create a cutting plane, choose the Z plane, and here's the mesh. So the first thing that we need to do is select the modules that we'll be using. And in this case, we use the centrifugal module and the flow module using turbulence and cavitation. This cavitation model performs cavitation and aeration analysis. The centrifugal module makes setting up the boundary conditions much easier as it presents the most commonly used conditions as a very short list, which makes picking very easy. The full array of boundary conditions are still available in the extended mode. It gives you a lot of extra options in extended mode, but the short list is in template mode, so we'll stay in template mode for now. To set up the centrifugal module, we note that we have 6 blades. It'll be going clockwise, and let's choose 3000 RPM and a rotational axis in the Z direction. So as we set this up, we can change any of these conditions that we want while the solution is running. You can change the boundary conditions and volume conditions while it's running if you like. This makes it very practical for virtual testing. Now let's look at the volume conditions. It's water. All of the default values are those of water, so this is already set. Let's look at the boundary conditions and assign the boundary conditions for the impeller, and we'll assign an inlet condition. This is the total pressure inlet, pressure of 1 atmosphere, and let's assign the volute outlet condition. You could see the list is very short here, so it's very easy when using the centrifugal template. It's very easy to assign boundary conditions, but if you wanted more, you could make those visible as well. So it's an outflow, and we'll specify a value. And next, we need to connect the two MGIs, the one on the impeller side and the one on the volute side. So we'll connect selector boundaries via MGI, and now they're connected. The last boundary condition will be the impeller wall, and we'll assign this as a rotor boundary condition. And you can see the rotor boundary condition is already set up because it's taking all of its information from the centrifugal template. So there's nothing that needs to be done in this boundary condition here except just to choose the rotor. Now I'm going to create a monitoring point so that we can monitor the fluid properties as the solution develops. And here you see the monitoring point is right at the periphery of the impeller blades. And I'm going to set up a plot so we can watch the pressure change as a function of iterations as the solution develops. Now for the cutting plane, we can select something to watch, and I'll select velocity magnitude. And so now we're ready to launch the solver. And here we've launched the solver, and you can see the velocity field beginning to take shape. And here we're monitoring the pressure at the periphery of the blades, and you can see that pressure is starting to stabilize and becoming linear, which means that the solution is converging. I'll go ahead and put in a couple of more plots. Here we have the pressure at the inlet, and let's add pressure at the outlet so that we can compare both pressures, and then we'll know the pressure difference across this device. And here's the pressure at the outlet in red. I'll add one more plot, and here we have the power that's required to run this pump. So this is the velocity magnitude. We can look at total pressure and total volume fraction. You can see here we're getting some cavitation here at the tip of these blades. So if you were to do traditional testing, probably wouldn't be able to see that you were having cavitation here until you got a part failure. But with PumpLinx, you can see that you would anticipate under these operating conditions that you would get cavitation. So you may want to vary your design. So now let's go back to SpaceClaim, and let's modify this to show you that when you re-import this into PumpLinx, that your model setup and all the boundaries conditions and volume conditions would still be as you set them up. This would be real useful. Supposing you might want to change the blade angles here to see if that would improve efficiency, or just make any other sort of design changes. You could do that very quickly, and then you would be ready to see the performance under these new conditions without having to set up the model every time. This particular geometry was originally created in CF Turbo. So I'm going to change this, a minor change. I'm simply going to extend this volute so that the outlet is farther away from the impeller. It's a minor change, but it's just to make the point that the boundary conditions, the volume conditions, model setup are all still there. So now we'll export this into Simerics, and this time we'll choose Replace Project Geometry. Again, I'll skip forward to the loading process. And here's the modified geometry. You can see that the volute tube here is longer than it was before, and we can take a look at the outlet. You see it still has the same specifications as it did before, as does the inlet and impeller wall. It's all intact. We simply replace the geometry. So this would be very useful as a design tool. You can very quickly make changes to your geometry in SpaceClaim and then reload it back into PumpLinx and do further analysis until you reach an optimal design. And this concludes this demonstration. In closing, let's review what was covered in this presentation. In the beginning, I talked about the advantages of the virtual testing approach using PumpLinx versus traditional laboratory testing. Here are some of the points that I made. Simulation results gives the investigator full access to a very wide range of data throughout the entire model, and there's no need for data reduction and similar manipulations associated with lab results. And when lab results, normally you only get data at a few points in the model. When you simulate, you can easily run multiple cases very efficiently as opposed to having to recalibrate and reset lab equipment. It's well known how difficult it is to get accurate results using intrusive measurement methods. You don't have this with virtual testing. Finally, virtual testing costs less. The demonstration began in SpaceClaim, where I showed how to prepare the model for exportation and gridding in PumpLinx. I then set up the model operating conditions and assigned volume and boundary conditions. Next, I launched the solver and set solution monitoring plots and a Z cutting plane so that the solution evolution could be observed. Lastly, I pointed out some of the flow field features. We could have easily set this solution up as a transient simulation with just a few more inputs. Please feel free to contact us if you have any questions.